We present ISBNet, a 3D point cloud instance segmentation network with instance-aware sampling and box-aware dynamic convolution. In a nutshell, ISBNet is a novel framework for 3D point cloud instance segmentation, 3DIS. First, we replace the clustering algorithm in existing 3DIS methods with a simple strategy to sample instance candidates with high recall rates. Second, we leverage the bounding box, deduced from mask annotations, as a strong geometric cue to further boost performance. Our method achieves new SOTA results on various datasets, including ScanNet v2, S3DIS, and SAPL S3D, and retains fast inference time. Here are the details of our paper. First, in the 3D point cloud instance segmentation task, given a 3D RGB point cloud, 3D coordinate plus RGB, we seek to obtain semantic and object instance masks of specific categories of interest. An example is illustrated in the figure below. We want to segment all instances of class chair and table in this point cloud. This task has a wide range of applications, especially where 3D point cloud data are the main source of input signal or complement the information provided by 2D images, including robot navigation, autonomous driving, and augmented reality applications. This task is challenging. First, in 3D point clouds, objects have much higher variations in appearance and shape compared to instances that occurred in 2D images. Second, 3D point clouds are unevenly distributed. Thus, it is not trivial to adapt standard 2D instance segmentation methods to the 3D domain. A typical approach for 3D instance segmentation is Dico 3D. Its architecture is presented in the figure below. It contains two main components, a 3D backbone and an instance segmentation head. The 3D UNet backbone is used for pointwise feature extraction. Next, to predict instance masks, it first groups points into clusters for object candidates. The clustering algorithm is based on a breadth-first search algorithm. Then, it generates an instance kernel for each object candidate. Finally, the core component is the dynamic convolution module. In this, it convolves each generated kernel with mask features to obtain a binary instance mask for each object. However, this method has two key limitations. First, the clustering algorithm usually misgroups points when similar instances are adjacent. For example, in the figure on the left, when multiple chairs are placed together, the clustering algorithm merges several of them into a single instance, the purple one, causing low recall object proposals. Second, in the dynamic convolution module, the appearance feature generated by the deep neural network is not discriminative enough to distinguish instances of the same class. To tackle these issues, we propose ISBNet with two novel designs. First, we replace the clustering module with our instance-aware sampling module. We sample a subset of k points where each point can represent a candidate object to obtain the final instance mask. With a specific strategy, these sampled points can cover almost all instances in each scene, thus yielding high recall object proposals. Second, we enhance the dynamic convolution with our box-aware dynamic convolution, in which we use the object bounding box as an additional geometric cue to improve appearance features. Our instance-aware sampling technique aims to efficiently select a set of k candidate points from an initial n points, where k is significantly smaller than n, while maximizing the instance recall rate. We employ two key strategies to achieve this goal. First, we utilize pointwise semantic segmentation to filter foreground points and exclusively sample from this subset. This ensures that the sampled points are relevant to the instances of interest. Second, we introduce a multiple round sampling approach combined with object mask prediction. Instead of sampling all k candidates simultaneously, we divide k into multiple rounds and perform iterative sampling. In each round, we sample points that do not belong to the previously predicted instance masks. To illustrate, in the initial round, we sample k1 points and predict k1 instance masks, as depicted in the figure. In the subsequent round, we exclude all colored points associated with these k1 masks and sample the remaining points. This iterative process allows us to capture masks of instances that were missed in the previous round, as indicated by the red blocks. By implementing these strategies, our instance-aware sampling method effectively optimizes the selection of candidate points, leading to improved instance recall rates while significantly reducing the number of sampled points. To enhance our box-aware dynamic convolution, we introduce a bounding box head that predicts axis-aligned boxes for both individual points, represented by the red block, and candidate objects, represented by the orange block. The underlying idea is that object candidates have the ability to influence points that predict similar boxes. In practice, we calculate the box difference, which encompasses variations in box size and center, between the pointwise box and the box associated with the object candidate. This difference is then concatenated with the appearance feature in the dynamic convolution. By incorporating this approach, we enable our model to effectively capture the spatial relationships between points and object candidates. This fusion of information facilitates the learning process and allows for more accurate mask predictions. We conduct experiments on 3 different datasets, including indoor datasets, ScanNet v2 and S3DIS, and the outdoor dataset, STPLS3D. For the evaluation metrics, we report the average precision AP and AP50 on ScanNet v2 and STPLS3D. For S3DIS, we additionally provide the mean precision and mean recall to compare with previous methods. Here, we show the quantitative results of our ISBNet and other methods on ScanNet v2, S3DIS, and STPLS3D. It can be seen that compared with our baseline, DICO3D, our method significantly outperforms by a large margin. Moreover, ISBNet achieves state-of-the-art results on 3 datasets, consistently surpassing recent methods, such as SoftGroup and DKNet, in all metrics. We visualize the qualitative results of our method, DICO3D, and DKNet on ScanNet v2 validation set in this figure. Each row shows an example with the input, semantic ground truth, and instance ground truth in the first 3 columns. Our method, the last column, successfully distinguishes nearby instances with the same semantic class. Due to the limitation of clustering, DICO3D mis-segments parts of the bookshelf in row 1 and merges nearby sofas in rows 2 and 3. DKNet oversegments the window in row 2 and also wrongly merges nearby sofas and a table in row 3. We conduct an ablation study on the impact of each component of our model. It demonstrates that incorporating either the instance-aware sampling or the box-aware dynamic convolution can achieve substantial performance improvements. Notably, when both components are combined, our ISBNet, it significantly outperforms the baseline by a large margin. We also analyzed the performance of different sampling strategies. It revealed that our multiple-round sampling strategy with 384 samples outperformed a single sampling with 512 points. We analyzed the runtime of our ISBNet and the other 5 methods. Our approach achieves SOTA performance while being the fastest, with a total runtime of only 237 milliseconds. The significant reduction is from our proposed sampling strategy, which is much more lightweight than other clustering algorithms used in these previous methods. That's it. Thanks for your listening. You can